Hello Precalc. We are continuing on with Chapter 2. We are doing Section 2-3, Day 1 notes. So continuity is something that we're going to be focusing on for this note sheet. And so what we're going to do is we're going to be looking at some graphs, which I need to draw for you. So let's say that you have a point at -1, 0, at 0, 1, at 1, 2. Let's say that you have a hole at 2, 3. All right, and so it goes down like this. Let's say that we have a point at 2, 5. And then let's say coming out of the hole, we just have this horizontal line like so. All right, so there's our graph that we're going to be answering some questions about. So we've got the limit as x approaches 2 from the left. So as we approach 2 from the left, we're getting closer and closer to that hole, which has a y value of 3. The limit as x approaches 2 from the right, so approaching 2 from the right, as we approach the hole from the right, we're still getting closer and closer to that hole, which has a y value of 3. The limit as x approaches 2 of f of x, well, since the left-hand limit and the right-hand limit are the same, it's going to be equal to that value, which is 3. However, f of 2 will be where it is actually defined. At f of 2, the y value is 5. All right, so those are some of the limits and answers for our graph. But then it says, is the graph continuous at x equals 2? Continuity basically means that you can go from one end of the graph to the other end of the graph without there being any disruptions. There's no holes, there's no vertical asymptotes, there's nothing disrupting the graph. It makes it continuous. Well, if we start on the left side and we work our way to the right, we end up having a disruption, that lovely little hole. So even though we have limits that are existing here, is it continuous? No. All right, because there's a disruption in the graph. This next one we're going to draw is we have a point at -1, 2. We have a point at 2, 1. And then our other point is going to be at 9, 7. And our graph is going to basically look something like this. All right, so there it is. And we're going to answer some questions about it. The limit as x approaches 2 from the left. So as we get closer and closer to 2, our y value is approaching 1. As we approach 2 from the right, so as we get closer and closer to an x value of 2, our y value is still approaching 1. The limit as x approaches 2, therefore, will be 1, because the left-hand limit and the right-hand limit are the same. And in this case, f of 2 is actually equal to 1. So notice this time f of 2 is equal to what all these lovely limits are equal to. That will make a difference down here. Is this graph continuous at x equals 2? Absolutely. As you go towards 2 from the left and to the right, it's not going to have any interruptions. So this one's a yes. Okay. What's going to happen is, in order for something to be continuous, here are the requirements. All right, if it is an interior point, like this one was, it's an interior point, what's going to happen is it will exist if the left-hand limit equals the right-hand limit, which they did, and f of that value is equal to what those limits were equal to. So we knew that the limits were both equal to, the limit was equal to 1 and f of 2 was equal to 1. That's how you know it's continuous. This one was not continuous because the limit approached 3, but when you got down to f of 2, it didn't equal 3, it equaled 5. So that's how you can tell whether it is continuous in the middle. If it's a left end, so if it's a point on the left, like this piece here, and we'll do an example, it will have basically, as you approach that point from the right, that limit should also equal f of a. And if it's a right endpoint, so over here, your limit as x approaches a from the left, so as you approach that point from the left, whatever that limit is, should equal f of a. All right, and I'll do some examples with all of these. We've got different types of discontinuity. So there's different types of things that are going to make it not continuous. One of them is called removable discontinuity, which means that there is a hole in the graph somewhere. So, something like this. All right? There may or may not be another point somewhere else, like directly above or below the hole. That may not be there, but you can see that there's obviously a hole. That's removable discontinuity. Jump is going to happen when you have maybe some kind of like a piecewise function, all right? So maybe something like this. That's a jump discontinuity. Infinite discontinuity is when you're going to have a vertical asymptote. So you might have, something like this. All right, that's going to be an infinite discontinuity. And then oscillating, not as important. We're not really going to talk about it that much, but oscillating, just so you know, is where you have all kinds of crazy up and down, but we're not going to have that. Okay, so we're not really going to talk about oscillating at all. Okay, so we're going to find and identify all the points of discontinuity of f of x equals x squared plus x minus 12 all over x minus 3. So there's obviously going to be some kind of discontinuity because of this lovely denominator. You can probably tell what it's going to be, but let's simplify this a little bit. If we factor this, you're going to get x plus 4 times x minus 3, and on the bottom you get x minus 3. So the x minus 3's cancel, which means that there is a hole at x equals 3. And they said to identify all the points of discontinuity. So hole, another word for that is removable discontinuity. So there is a removable discontinuity at x equals 3. All right, and that would be your answer for that particular problem. So we're just identifying where it's discontinuous. What we're going to do next is we're going to use the same function, and it says give the extended function. All right, so what we're going to do is we're going to come up with a function. It's usually going to be a piecewise function so that it kind of fills in the hole. All right, we want to make it continuous. The goal is to create a continuous function. So what we're going to do is we know that our function is this x squared, I'm going to make a piecewise here, x squared plus x minus 12 all over x minus 3. It's continuous everywhere except for x equal to 3, because obviously that makes it undefined. What we want to do now is find this piece that's going to go down here that will create, it'll fill in the gap. So we know that there is going to be a hole at 3. Let's figure out what the y value is. So if you plug in 3 after the x minus 3's are canceled, you're going to get 7. So there's actually a hole at 3, 7. So what we're going to do is we're going to fill in that hole. We're going to make our y value 7, and we're going to say that's going to happen when x equals 3. All right, and so then that way we'll create a point at 3, 7 to fill in the hole. All right. For number 3, we want to find all points of continuity and discontinuity of the function, and we're going to identify the types of discontinuity. Is it possible to write an extended function? Okay, so let's look at this guy. If we look at this function, all right, there is going to be discontinuity when x equals -2 because there is a vertical asymptote at x equals -2. Plug it in, you're going to get 0 in the denominator. So the point of discontinuity is going to be x equals -2, and because it's a vertical asymptote, that's known as an infinite discontinuity. All right, so x equals 2, there's an infinite discontinuity. All right. And then it says, is it possible to write an extended function? Here's the hint with that. You can only extend functions that have holes because it's really nice and easy just to fill in a single point. Because this is a vertical asymptote, there's no way to fill in that gap. So the answer is going to be, well, basically, let me write this. So you can only extend functions with holes. With holes, or another name for it, removable discontinuity. If you have a hole, then you can write an extended function. Because this is not a hole and it's a vertical asymptote, the second part of this, can you extend the function? No. you cannot fill, because we're trying to fill in the holes, you cannot fill an infinite discontinuity. You can only do that with a hole. The hole is nice and easy. Vertical asymptote, that leaves a huge gap. Discontinuity. All right. So there's no way to extend the function. All right. Let's see. For number 4. Number 4, we have find and identify any points of discontinuity. Give any formulas for the extended function. So what we're going to do is we're going to simplify this a little bit. All right, remember your difference of 2 cubes formula. This is going to factor out to be x minus 1 times x squared plus x plus 1. And the bottom is the difference of 2 squares, x plus 1 times x minus 1. All right. And we notice that the x minus 1s are going to cancel. So we know that at x equals 1, there is a vertical asymptote, which means that there is a removable discontinuity. There's a removable discontinuity. Since there is a removable discontinuity, at x equals 1, we know that there is a way to extend the function. So the formula for the extended function will be the piece that's left over. So it's going to be the y equals, or f of x equals, y equals x squared plus x plus 1 all over x plus 1. All right, so that's going to be the first part. However, there's also going to be another part of discontinuity right here at -1. When x equals -1, there is a vertical asymptote. So at x equals -1, there's a vertical asymptote, which is known as an infinite discontinuity. There's infinite discontinuity. And because there's infinite discontinuity, there is no extended function possible. All right, you can only have an extended function if there is a hole or a removable discontinuity. For this particular one, there isn't. Okay, the last piece, number 5. We'll see if we can get through this in 15 minutes. You're going to give a formula for the extended function of f of x equals cosine of x minus 1 all over x that is continuous at x equals 1. So what we want to do is we want to come up with a function. All right, it's going to end up being kind of like the top problem, number 2. We're going to have a formula. It's going to be a piecewise formula. What we're going to do is, if you look at this guy, all right, it might look like there is a vertical asymptote at x equals 0. However, if you plug in 0 into the numerator, you'll have cosine of 0 minus 1 all over 0. Cosine of 0, if you remember, is 1. You're going to end up with 0 over 0. So there is actually a hole at 0. If you graph this function on your calculator, you will see that as you approach 0 from the left and the right, it's approaching 0. So there's actually a hole at 0, 0. All right, and you can see that just by looking at the graph on your calculator. So what's going to happen is the one part of the function will be the cosine of x minus 1 all over x, as long as x doesn't equal 0. Okay, because x can't equal 0 or it makes it undefined. Now, because there is a hole at 0, 0, what we're going to do is we're going to make it so that the y value is 0 when x equals 0. This second piece always kind of fills in the hole so that it is continuous, just like we did with number 2 at the top. So that is it for continuity. I was able to fit it into one video. How about that? So yeah, that's it. Thanks for listening.